Okay, welcome class. Last topic from chapter 4 of journal 3. So just about done this journal. And pretty easy ideas here is that we can actually use a double integral to get an area. And we can use a triple integral to get a volume. We had been using single integrals for area and double integrals for volume, and we're just showing that another special case of that, I guess. So if I took the double integral from 0 to 4, x to 2x of dy dx, so I actually had no surface there. Really, that's representing an area. And why is that the case? Because there's really like an invisible one here, right? And this is showing, well, let's talk about the limits of integration and what the region looks like. So the region R in the xy plane would be, these are y equals limits on the inside. Y goes from x to 2x, from 0 to 4. So say that's 4 along the x. That would mean we're getting this section. This would be the 0.48. So we're getting the, if I do this, what we had done up to this point, this was a volume over this region to a surface. In this case, there's really like an invisible z equals 1 surface, which is, because the z-axis is coming out from the board, that would be this horizontal plane where we're back in our usual orientation, but in this orientation, it's this z equals 1 plane. And we're going from that surface to the region. And so we're actually getting a geometric object that goes from this surface down. So it has these like vertical walls, and it has a height of 1. And then the volume would be the area of this base times the height of 1. And so we're just trying to, enjoying that and getting that volume, that's exactly the same as getting the area of this region in the xy plane. So when it's done this way, if your surface is an invisible 1, this is exactly the same as the area of R. So maybe it's a little bit more complicated way of looking at area, but what you did back in Calc 1 or 1.5 or so is you would get this area with a single integral. You would say this is the area between two curves, the curve y equals x and the curve y equals 2x. And you would do an integral from x equals 0 to 4 of 2x minus x dx. Well, that's exactly the same place you would get to if you work this double integral from the inside out, right? You'd get, let's go ahead and do it. 0 to 4 dx. On the inside, I'm integrating 1 with respect to y, and I get y. I'm going to evaluate at y equals x to 2x. 0 to 4, upper limit minus the lower limit dx. Right. So maybe this is a more complex way of doing the single integral, but the double integral really represents an area. And sometimes that's helpful to see, and you're going to get a lot of practice with thinking of those as areas, and then making sure you can switch the order of integration from x to y. It'd be easy to do in this one, but there's some examples for it. It takes a little bit of ingenuity or creativity to think about how to do that. And we saw in the last video why you want to do that. Some reasons are the integrand is easier to integrate one way than the other. Other reasons are that the region is better defined as y equals or as x equals. Those are the main reasons why you may want to switch the order of integration. So double integrals can represent areas. In the same way, triple integrals can represent volume if the function, in this case, w would be a function of x, y, and z when you're doing triple integrals. If w is just an invisible 1, and then you're integrating, say a dz dy dx, then what you're getting is a volume. if there's anything other than 1, you're not getting a volume, you're getting something in higher dimensional space because you really have an R4 surface. You can't visualize it, but it does have a lot of physical applications, and you'll get to that in your majors, in physics and astrophysics in particular. Okay, so maybe we'll just work one more problem for this section, otherwise it's pretty short. Suppose they give us a surface that lies between these two functions. Okay, so we want to get the area of the shaded region. We have these two curves, one's a y equals, one's an x equals. Both easy to solve for the other variable, though. And we could set up this as a double integral just to practice. We could do it as a dx dy or dy dx. And there's this invisible 1. If we do it as a dx, and then we'll maybe put it over here, dy dx. If we're doing it as a x equals first, we look at the region and we say as we go from left to right, does it always stay from one function to another? Yes, it does. Every little sliver would go from the parabola y squared minus 2 to the other parabola x squared. And so we just say we'd start with the y minus 2 squared, and then we go to this, which is equivalent to x equals the square root of y. We're just doing the positive part there. And then we'd say y goes from, and we have to get these points of intersection from there to there. On the other hand, and so we can do that by solving. We'll come back to that. On the other hand, if we did this as a dy dx, we would start going this way, and we'd say as we go from bottom to top, does it always stay between two curves? And it doesn't, once again, right at the split here. It does on this side. It always goes from y equals x squared to the other parabola x equals y minus 2 squared. Whereas over here on the left side, we'd have to do some more work to kind of, again, split this to this function to this function, this line to this parabola. For that reason, this one is more work. This one's the harder one to do. It makes sense to write it as a dx dy. Okay, then the last piece of this puzzle is we need to get these limits of integration. I don't know if my picture's drawn to scale either. So let's see what happens when we solve, sorry, the points of intersection are the limits of integration. Okay, so y equals x squared, it's easy to solve for x. So we'll say x equals the square root of y. Now we'll set the two x's together. Square both sides. Now we're going to have a quartic equation. So we'll simplify that out, and then we can ask for a solution to that. So it's going to be y minus 2 times y minus 2 times y minus 2 times y minus 2 equals y. So we'll do some FOILing here. Y squared minus 4y plus 4 times y squared minus 4y plus 4 equals y. Lots of distributing. And you're going to get the highest power. So it'll be a quartic equation that we can't solve by hand. It's not going to be, I can tell right away, it's not going to be a nice one. So we can plug that into a tech tool to solve, to get the roots, or we could just graph the function associated with this when we set it to 0 and get the x-intercepts. Those would be the roots. Those values will go right here as our limits of integration. And then we're working that problem just as you would inside out, or it really turns into a single integral that represents the area between two curves, but just written as x is a function of y functions. Okay, so let's solve this. Use Wolfram Alpha to do solve y minus 2 to the 4th minus y equals 0. See what kind of limits we get. Y minus 2 to the 4th minus y equals 0, okay? Again, we'd expect at most 4 roots, and we do see, again, this crazy quartic equation that was used. Here's a plot of the real roots. There are some complex ones, again, not things that we're going to deal with. So we see 1 and 3.35 are the ones we're interested in here. So this would be at 1 and 3.35 about. So those would be our limits. Not hard to do those integrations by hand, plug in, okay, there's some decimals, but just to show you one more time that while we're at Wolfram, there is a double integral tool. So it's called a calculator, double integral calculator. And we'd want to be integrating 1. And we do have domains. So we want to enter our limits of integration, which are, and just to show you here again that you can have variables in your limits of integration. We're starting with x. X goes from y minus 2 squared up to square root of y. And then y goes from 1 to 3.35. Again, you carry more decimals, but we're just doing it quickly here to show you how the tool works. Check that it did the right order, and it did not, so I always get this one mixed up. What it calls the variable 1 or variable 2 isn't intuitive to me. Wish it would say like inner variable outer. So I need to flip-flop this and say that x goes from y minus 2 squared to square root y, and then y goes from 1 to 3.35. And let's see if this, look at the way it's interpreted, your input, definite integral, I want the x first, inner limits are y minus 2 squared up to square root of y, that checks, outer limits are y's from 1 to 3.5, and it gets a value of about 2.27. And it's saying that that would be the volume if there was a z equals 1 plane over this, the volume of from this sort of I-shaped thing up to the plane z equals 1, or it's also just the area of what is here in the xy plane, and that's about 2.27. Two ways of thinking about those double integrals then. Okay, that is the last topic then in chapter 4. So actually one more thing, we are going to, there's one more thing in here. Surface area. And surface area can be done with integration as well. We're going to come back to surface area in book 3.5, so I just want to show you the formula and we'll talk about the derivation later. It's going to be double integral, just like we've been doing, over some region R. We talked about how to define it. And then there's this formula. Okay, depending on your region, you'll do a dx, dy, or dy, dx. That'll affect how you set up your limits of integration. In general, we just say over some small area dA over that region. And what we have to do to get the surface area is the square root of 1 plus a partial with respect to x squared, partial with respect to y squared. Clearly, it probably is obvious to you at this point that this is a messy, and only for like the easiest, simplest geometric objects for which we already have formulas to get surface areas is this really helpful. You're almost always going to need some tech tool that does numerical integration. Again, 245, really cool class. Math 245, Math 545, our graduate program, you'll see how computers are actually doing these algorithms to approximate this. Again, in book 3.5, we're going to have another way of looking at this, getting to the same formula, but we'll do the derivation. And it really comes from the fact that we're going to think of any surface, some surface. We want to get the area of this surface area, and we're going to divide it into a bunch of tiny little tangent planes, little segments of tangent planes at points. And we're going to make those tangent planes get smaller and smaller. Again, approximate, refine, limit. That idea happens over and over. And as we do that, so you can think of this surface as actually made up of a geometric approximation, which is little segments of tangent planes. But we don't know how to get those areas of tangent planes in an easy way now. We could do it, but it's a give it a work. It's a very easy way in book 3.5 when we learn about vectors, well, two vectors, that'll make a parallelogram on this surface. So connect the rest of the parallelogram, imagine doing that. And we're going to just take a really small little parallelogram and a whole bunch of those. And it's easy to get the area of those parallelograms once you know about vectors in book 3.5. So we're getting there for the derivation. That's coming. For now, I guess one more comment I'd like to make. Besides the fact that they are going to be messy, and the variation is coming, it really makes sense, is that maybe this reminds you, if this part wasn't here, what does that remind you of? Pause the video, take a moment to think about it. Hopefully remember this is going back maybe a couple calculus classes, either the end of Calc 1 or maybe the beginning of Calc 2, you learned about arc length. This is the arc length formula when we have a single, sorry, I should say that, a single integral that expresses an arc length. And so back to our surface, again, think about the derivation here is that there is some, you can think about this as having like slices through it where this string and the string is moving in ways that are parallel, keeps moving along. And each time I take that sort of slice through it, I'm getting an arc length. And then I'm going to sum those up. So I'm going to get arc lengths, and then I'm going to do that as I sweep through the surface. So that's the relationship between arc length and surface area, and why those formulas look similar. I hope that'll help you remember it too, until we get to the derivation, and then that'll hopefully sink in really well. Okay, that's the end of book 3. In chapter 4, the end of chapter 4 has some really interesting, I think there's 3 or 4 challenge problems at the end there. Really interesting, in particular the upgrade. So I want to challenge folks to challenge yourself. If you got time and you can work with another partner, work by yourself, if you want to do some extra upgrades, always bonus. If you got time, have some fun and look at some of those. There's some real doozies in parts of those, and some of them are going to require a tech tool. So if you get working by hand and you say, you know, they wouldn't make me do this kind of calculation, and a lot of times it's not even possible to do this. So model it, visualize it, verify it, jump to a tech tool, and then make sure that what you put in there, that your model makes sense, that the results you're getting out make sense. Okay, well, hope you have fun. And then on to book 3.5, some really cool stuff there.